So I'm Greg Bryan. I'm at Columbia University, and I want to just tell you a little bit, give you a brief overview of a project that we're just trying to start up. So this is a Simon's collaboration, as it says, to try to learn the initial conditions of the universe, broadly speaking. And so this is a collaboration amongst a wide group of people. So it includes people who do fluid dynamics, galaxy formation, that sort of thing. People who do cosmology, machine learning. You guys, but also statisticians. So we're trying to bring all these people together. They did like Shirley is doing with this conference to focus on a set of problems. So what are those problems? Well, they're very sort of grandiosely put here. What's the composition of the universe? What are the sort of initial conditions of the universe? But also how do galaxies form, and how do they map out those cosmic structures? So more concretely, the project's goals are to infer not just the cosmological parameters, but also the initial phases and amplitudes. So this is, on the left-hand side is this little figure, which is designed to show the amplitude, the initial perturbations or the early perturbations, not just at the surface of last scattering, but throughout the volume in which we can try to infer them. So as you all know, the universe does this through some sort of forward model. It takes it's somehow managed to create a universe which is complicated, has lots of galaxies, has cosmic microwave background, but also potentially lots of other observables. So this project is initially going to focus on the distribution of galaxies. So in particular, the distribution of Sloan galaxies, but also the cosmic microwave background, in particular, observations of ACT. So as we've heard, I think a number of times here, this is really an inverse problem. Inverse problems are hard, but in principle, we know how to solve them. We forward model them. Take samples of the parameters, both the cosmological parameters and the initial many different initial conditions. Forward model them, compare to the observations, and compute a likelihood. Repeat the process to get a posterior distribution. So great, but of course this is a big problem, as I've just described it, both because what we want to really try and do is map out the distribution of the galaxies and the gas, and so we need to do this forward model by potentially running very large scale simulations, so things like TNG or Eagle, but in much larger volumes and with many different versions with different parameters. So that's one, and of course that's TNG took much computational effort, so that's a very challenging process. But even if we could do that, of course we can't write down the likelihood in the full likelihood, so our approach is really, we've mapped it out in terms of 3 distinct projects to address 3 parts of that process. So the first part is to develop really from the ground up numerical models which faithfully reproduce galaxy formation, galaxies, and their gas, not by calibrating to observations, as is the common procedure now, but by basing these simulations on basic physics and on smaller scale simulation. And then take those simulations, use them to train machine learning techniques to accelerate them, and then use that as part of the process which I just described. So this is timely, we think, because first of all, as David said in his remarks this morning, there's a lot of data coming down the pipeline towards us, and we'd like to be able to use it effectively and efficiently. Second of all, and maybe this is something for this group that I think is important, which is that galaxy formation simulations are really beginning to mature. When I did my PhD thesis a long time ago, I initially wanted to work in galaxy formation, but then as I began to learn a little bit more about how complicated galaxies are, I decided to flee from that field, and I left and I did lots of other things. But now coming back, I think galaxy formation is really at a point where we can make these sorts of predictions. And then finally, of course, machine learning is this unfair advantage that we can bring to this problem. So here is an overview of the project. And I'm going to go through this in a little bit of detail, but basically it's a flow chart mapping those three different projects. On the left-hand side here is the, in blue are these numerical simulations, these actual computer models, which are going to predict the distribution of all of the stars and the gas and their observational consequences. In green, the machine learning accelerated version of those, and then this inference process. So this first project, actually, I'm going to entirely skip over. I'm going to leave it for Rachel Somerville to talk about. I think there's lots of interesting work there, but let me, so I'll leave her to describe this forward model that we're going to, this actual simulated forward model. And instead, I'll focus on projects 2 and 3. So project 2, which is to take those models and learn from them and develop machine learning algorithms. So our initial plan is to do this in 2 steps. So the first step will be to create a dark matter distribution based on the initial parameters and phases. And then as a separate step, so as a second step, we'll take that dark matter distribution and then develop a fast forward model to directly predict observable galaxy properties and other things like the hot gas distribution, for example. So to do that, we'll use something like camels that Paco and Shai and Daniel Angles-Alcazar have developed. A modification of camels using the simulations, these new simulations that I was describing, and these outputs and synthetic observations. So what does this first part look like? Well, I don't want to go into a lot of detail because I think we've been hearing about it over the last few days. And I just put up one example, but there were a number of talks earlier which develop neural network representations which can predict, hopefully accurately, and generalizably the distribution of dark matter halos and dark matter, full distribution of the dark matter. Next steps in that process are to produce not just the positions of the dark matter particles, but also their velocities. Make sure that this is generalizable. And right now we're limited in size. So what we'd of course like to do is use low resolution simulations and then train higher ones to predict the small scale structure. And this is a paper from work from Yin Li and Shirley and others, showing that this is at least in principle possible, that we can augment these low resolution simulations, which are trained on higher resolution simulations, to produce realistic looking dark matter distributions, which then we can add baryons to. So that's the second part of this machine learning, this forward acceleration. And I'm not going to say a lot about that either, except to say that there's promising work on that as well. Of course, there's a long-standing history of this with halo occupation models and things like that. But here we'd like to base this on machine learning, and so so one example, which I'm actually not going to go into, I can talk a bit more about, is work to predict the galaxy's stellar masses, for example, and hence their resulting luminosity, which then could go directly into the catalogs and be compared to observations. So, assuming we manage to get that that work done, and I just want to say that so initially we were planning this two-step. But maybe eventually one could go from the initial distributions directly to the galaxy properties, combine those two things, or even go to the observations directly. But assuming one can do that, then the next step is to take those observations and use them in an inference pipeline. And there's two parts, so we're going to explore two ways to do this. One is a sort of traditional explicit likelihood inference technique. It's been around actually for some while. It goes under the name of Borg. And it's something that we know works to at least some degree, although we're going to augment it by incorporating some of the results from the simulations. But I think what's really interesting and exciting is these simulation-based or likelihood-free inference techniques. So let me just first of all describe the explicit likelihood technique. Of course, reviewing this is we use this double forward this machine learning emulator to get to the observations compared to the likelihood, and then use some sort of Markov chain with this Borg technique to constrain both the parameters and the initial conditions. And so this is sort of a quick overview of what this process looks like. And this largely exists right now. So we're going to make some improvements to this process because this process from 1 to 2, for example, is done in a very in the current Borg implementation is done in a fairly simplified way, as is from 2 to 3. So we think we can improve, particularly the first part of this by using this machine learning accelerated gravity and hydro models that I just described. And just as a proof of principle here, this is some work done by Guillaume Lavaux and Jens Yashi, which uses Borg to based on an existing galaxy survey, small one, to get to infer the initial conditions, and what's been shown here is just different possible versions of this. So that's the technique, the safe technique, the one that is we're still working on, or is potentially more powerful, is the simulation-based inference technique. And we're exploring a number of different ways to do this, or we're going to explore a number of different ways to do this. One example is through these compression techniques to create, so the power spectrum and various things, peak counts for lensing, for example, are various different ways to compress the data to get summary statistics. But it would be very nice to allow the machine to determine what are the optimal or near optimal summary statistics itself, and then use that to compute the posterior distribution. And maybe that can be done directly using some sort of neural density estimate. So, and here's an example of this, again, from work by Guillaume and Ben Wandelt and others, to use this, an example of, I won't go into it, you can read it a bit, but the idea is to use this to develop these sorts of optimal compression. So lastly, we want to emphasize, and I think there's supposed to be discussion on this, that throughout this process, we want to look carefully at the robustness of the inference as we go along. There's a lot of things which can go wrong in the steps which I just described. The simulations are still not perfect, even once we include all of these physical effects. We think the forward learning, the forward modeling can have errors in it, misgeneralization, misspecifications, generalizations that are not accurate. And so we want to carefully explore ways to find out if this is all robust, and try and work on interpretation, so things like symbolic regression. So how does this all fit together? So here's the project plan all put back together again, and who's going to do this? So here are the PIs, and also, as I said, so it's 8 institutions plus the number of people at the CCA. And actually, this is missing one important person. So David Spergel has joined the collaboration, so I've mapped those people onto very rough estimate of sort of where they are in this process. So you can, I think, we're going to be starting this collaboration up in the fall, and so we'll be hiring, and many of these people, not all of them, but many of these people will be putting out job ads. So those I encourage you to help us in this process of trying to learn the universe. So thank you.
Okay.
Thanks for the talk. This looks like such a wonderful plan. When it comes to analyzing data, though, actual observations, the devil's in the detail. And I noticed in the diagram there's no one dedicated to understanding observational systematics and how to either emulate that or forward model that into this whole pipeline. Have you thought about that?
Yeah, I think that's a really good point. I think you're absolutely right that the devil is in the details. I mean, I think I'd say two things. One, I didn't spend much time talking about. We have given some thought to the observational production of mock observational catalogs and CMB maps. I think it would be fair to say that our approach to that is still in flux for exactly the reasons that you mentioned. I think that is a very challenging aspect, and I think we're still trying to understand where we want to end and where we want to work with other groups who are better at that or collaborate. Yeah.
Questions?
Summary statistics, and in a sense linked to this question about systematics, which have people identified summary statistics that in principle should all be 0 if the systematics are not in the data. And an example that comes to mind is if I look at the initial conditions and look at the isotropy of the initial conditions. that finding some, if I reconstruct my initial conditions so that all the density fields point towards the, our galaxy, then there's something wrong with our initial conditions. So that you can imagine constructing a bunch of statistics that we know should be zero, right? That the galaxy density field correlates with the direction in which the survey was done, right? Or the sky directions. There's lots of observational systematics. And I've wondered whether summary statistics have been used with systematic summary statistics, things that we know ought to be zero if they're correctly, if the analyses were done correctly.
Yeah, that's a great question. So of course, null tests have a long history of in this field and others. But I think this automatic production of summary statistics, for example, that I mentioned at the end, is one that optimal summary statistics is one that I'm have some ambivalence about, right? Because I mean, potentially it's very powerful, but then you're putting a lot of trust into the creation of those. So I think it's such a good question that actually probably what I would do is turn it over to the audience, who are probably better positioned for the most part to answer it than I am. I would love to know if any of you have been thinking about this.
I know being moderator, I'm not supposed to talk too much, but Chang, Hoon-Han, and a bunch of us and Michael Eckenberg working on sort of like putting in all the systematics of Sloan, for example, into a pipeline. And I think Chang can talk more about this. And I think for this group of people, I mean, Rachel, Simone, and I both work closely with the data. So, but we're hoping to hopefully recruit more people to join our mission, I guess. That's how I'll phrase it.
Yes. All right. Please.
I can say one thing we've done, and I think it should be more common. There was a lot of emphasis on beyond Gaussian things, measuring.
I think we can't hear you.
Yeah, there was a lot of emphasis in going beyond Gaussian statistics and doing either with statistics or with machine learning. A good null test is to feed Gaussian fields to these, and that should be zero. And I don't think it's done very often.
Yes.
I mean, I don't. It can be done in many contexts, but just generate some Gaussian field and apply your favorite non-Gaussian statistic with.
Right, and to make sure that, for example, if the data is comes from a power spectrum with linear power spectrum, that yes, that you don't get anything else besides that the machine learning and the Gaussian statistics.
Well, it's especially for machine learning where you're not even sure what you're measuring. Gaussian fields.
Yeah, no, I think that's right. I mean, that's one of the reasons I emphasized at the end this robustness question. We're very aware that that's an important concern.
That's fine. Yeah, so about the systematic, I think as long as we have a set of summary statistics, right, living in a high dimension space, and basically you have a covariant matrix for distribution and cosmological dependence. So the cosmological dependence only define kind of a subspace in this high dimension space. So any kind of deviation from this subspace will be systematic. So it's kind of, I think, it's not very hard, right? You can check any possible deviations from the subspace defined by realistic cosmology, as long as you have a set of summary statistics.
Right. No, I think that's right. I think one just needs to be conscious and of the possibility and to do it.
Yeah. Okay, just one very fast comment, all right? Because we're really running late.
it's more of a comment than a question, but like I was a little nervous about, I see a lot of machine learning going in like literally every step at that point. And the one thing that makes me nervous in this sense is if you can check independent steps where you have put ML with like other traditional methods of analysis. But I was wondering if there is something that would be checking the entire pipeline after you have. Because one thing that's not obvious to me is that if I replace component A with ML and then I check that robustly and component B with ML and check that robustly, then the combination of that whole thing will still be equally robust. Because most importantly, because like I do not know what things I have missed in checking A, and that might be picked up with B, and so on and so forth. So I was wondering if there was any plan or thought to like compare this whole pipeline where I have machine learning entering at almost every step with any other.
In software engineering, people distinguish between unit tests.
Yeah.
Test a particular unit, and answer tests, or pipeline tests, which test the entire pipeline put together.
Yeah.
No, I think you're right. I mean, these comments are particularly useful because we're at the early stage. We haven't started yet, really. So I think that's an thing to take on.
Again. Next up, we have Rachel telling us more about this collaboration.
Thank you. So I want to really thank the organizers for putting this conference on. I've really enjoyed it and I've learned a lot. And I think in the spirit of people from disparate fields talking to each other more, that this has been a really great experience. So you all know this, but I just wanted to remind you why simulating galaxy formation is so difficult. So, of course, galaxies are shaped by a huge variety of physical processes, from gravity to thermodynamics, hydrodynamics, radiation, perhaps cosmic rays, et cetera, magnetic fields. And galaxy formation is a devilishly multi-scale problem. So we care about processes occurring on megaparsecs to tens of megaparsecs, like structure formation, accretion of gas from the cosmic web into halos and galaxies. But then the properties of galaxies and the gas surrounding them out to quite large distances, as we've seen, can be affected by black holes forming on scales of less than a parsec, or supernovae exploding on these very small scales. So understanding how all of these scales interact with one another is, perhaps the big challenge for galaxy formation, as with many fields. And so let me give you a little view of kind of the state of the field. This is a nice diagram that was put together by Dylan Nelson. And what this shows is on the x-axis is the number of galaxies, or on the top, the simulation volume. So I hope you can read this. This is 10 to the 2, going up to 10 to the 8 at the right corner. And then this is the baryonic mass resolution. And this is sort of confusingly backwards. So the top of the plot is a lower number, which is better resolution, right? And so at the top of the plot is 1,000 solar masses. And as you all know, there are a range of different points in this space that we can sample with the finite amount of memory and finite amount of computational time that we have access to. So you can either do a couple of galaxies, perhaps what we call zoom-in simulations at very high resolution, with relatively explicit implementations of these physical processes that I mentioned. Or at the other end of the scale, you can do a very large volume, but then of course, at lower resolution. And of course, with that lower resolution, you can no longer treat the physics explicitly. And so you have to resort to these dreaded subgrid models. So what we want to do for the Learning the Universe program basically requires doing gigaparsec volumes, preferably with physics that is as explicit as possible. And we need to do that thousands of times, right? So that's sort of, off in the corner of the room. And so this, of course, is why we need machine learning to help us. So just to say a bit more about our philosophy, Greg already mentioned this. So traditionally, of course, these subgrid models tend to be quite phenomenological, and then they are tuned to match global galaxy observations like stellar mass functions, et cetera. So we want to take a different approach and instead drill down using a ladder of multi-scale simulations to really understand how these physical processes work at the scales where they are acting and how they interact across different scales. Then we want to use those simulations, perhaps in some cases idealized simulations, as laboratories to develop analytic scaling relations that can form the basis for new physically grounded subgrid models. And then we may still have some parameters remaining in those models, but instead of tuning those to match observations, those have to be calibrated to higher resolution or more physically explicit simulations. And another very important piece of our philosophy is that any validation has to exploit multiple probes. So, gas, stars, different wavelengths, observations, and should be carried out in the observational plane, accounting properly for the observational effects, just as Chang pointed out earlier. So let me just give you a couple of brief examples of how this actually works in progress. So we've started doing some of this work as part of the SMAUG collaboration, which many of you may have heard about, which stands for Simulating Multi-Scale Astrophysics to Understand Galaxies. So we've been working with Ivo Stryker and Chang-Gu Kim and their group, who have built these beautiful simulations called Tigris, which represent a small piece of a galaxy. So these are what are sometimes called tall box simulations. And they can explicitly resolve the Sedov-Taylor explosion of supernovae and actually measure how these multi-phase winds develop and push gas out of the galaxy. And so what Chang-Gu and the rest of the SMAUG collaboration have done is to use these simulations to characterize the wind launch properties. So for a given amount of supernovae that have gone off, how much mass, how much energy, how many metals are ejected in these winds, what is the velocity of the winds, what's the phase structure of the winds. And as you might expect, these winds are quite complex. So on the right is shown on the x-axis the velocity of the wind material, and on the y-axis the sound speed. And so you can see that there's no single velocity that characterizes these winds. There's a broad range of velocities. The winds are multi-phase. Most of the mass is carried by the cold phase. Most of the energy is carried by the hot phase. And so the whole method for implementing the winds has been guided by these studies of these detailed simulations of how winds are actually driven in the ISM. Then another example is once these winds are launched, how do they interact with the circumgalactic medium as they propagate outwards? So you can imagine this cold, dense material interacting with the hot, lower density material, and what governs the evolution of these cold clouds is largely these Kelvin-Helmholtz instabilities that develop at the interfaces. And so we need to understand how mass, energy, and momentum are exchanged between the hot and cold phases as these winds propagate out of the galaxy. So again, we can use idealized, very small scale simulations. So these have been carried out by Drummond Fielding and collaborators to understand how the gas mixes in these turbulent radiative mixing layers. And so there's some very nice work by Drummond. And then recently, Drummond and Greg have developed an analytic model to describe this process. So then we can put these pieces together into something we call Project Arkanstone. The Tolkien fans may remember that the Arkanstone was Smaug's favorite jewel, favorite treasure. So this has been led by Matthew Smith and Drummond Fielding. So we combine these wind launch properties from Tigris to spawn wind particles, treating the cold and the hot phases separately, So the hot phase winds have to be represented with much smaller mass particles, for example. And then we use the turmoil model, this stands for the turbulent radiative mixing layer model developed by Drummond, to describe how these particles exchange mass energy and momentum with the surrounding medium and recouple into the circumgalactic medium. So this is currently being implemented within the Arepo code, but it's being formulated quite generally so that in principle it could be implemented in any hydro code. And we're currently in the process of carrying out both sort of idealized tests like a Chevalier and Clegg wind, and also working on implementing this within an idealized isolated Milky Way-like galaxy. So then one of the big challenges, of course, for the continuation of SMAUG and learning the universe is to carry out similar exercises for the even more challenging problem of how black holes grow and how black hole feedback affects galaxies and the surrounding gas. But we think that we can use a similar philosophy and similar approach to try to tackle this problem. And I'm showing here results from 2 papers from the SMAUG collaboration that you can check out if you're interested. How am I doing on time, Shirley? I'm good. Okay, great. So one of the major goals, of course, of learning the universe, as Greg has mentioned, and as we've discussed, is to develop machine learning-based techniques to accelerate these physics-based simulations. And so we need to create mappings between the dark matter particles or halo properties and the gas density and temperature distributions and galaxy properties. So we've already heard at this meeting about very promising work where the full particle distribution has been used, for example, to predict the distribution of the Lyman alpha or H1 gas. So this seems to be very promising. But as we start to look at these much larger volumes, a question is whether we can instead just use the dark matter halo properties. Of course, this is much less data intensive, it's much less data. And if we think that galaxies form in halos, then you might think that the halo properties might be enough to allow you to predict the galaxy properties. So there's already been, of course, some work along these lines shown on the slide here. So some example input features you could imagine, of course, the halo mass, velocity dispersion, concentration, spin, environment, assembly history, et cetera. And then typically you'd like to predict an ensemble of galaxy properties, either sort of intrinsic properties like stellar mass or star formation rate, or ultimately we'd like to predict observable properties such as luminosity in a set of filter bands or a particular line luminosity. So I think that these efforts have just been starting, and I think there are still a number of open questions, such as what are really the best or minimal set of input features to use to learn a specific set of observables? How accurate can these techniques, what accuracy can they achieve? And what is really the best machine learning approach to use for this problem? So I'm probably out of time by now. I have a few minutes. Oh, I'm almost perfectly out of time. So I'll just mention that we've started working on this problem with a graduate student from Columbia, Avery King, and Kim and Greg and Shirley. And I'll basically just, I'm happy to tell anyone who's interested about our very preliminary results. But let me just, in the last negative few seconds, tell you some of the takeaway messages that for me were a little bit surprising. So certain properties like stellar mass can be learned to a fractional error of around 10%. So if you ask, for a particular halo in the median, how well can you predict the stellar mass? So that's pretty good. But then other properties like the cold gas mass or molecular gas mass or the star formation rate are much more difficult to learn. So they can only be learned to maybe 20, 30, 35% accuracy, at least with the methods that we have tried and the input features that we have tried. We found that adding information about the assembly history significantly improves the accuracy. That's not too surprising. We found that neural nets did perform better than extremely randomized trees, so decision tree-based methods, which had been more widely used in the literature. We've also found that all of these methods are not able to correctly predict the dispersion around the median relations. So even when they can predict the medians pretty well, they don't predict the dispersion correctly. And if you imagine this set of galaxy properties, mass, gas mass, star formation rate, et cetera, we know that there are these fundamental plane relations, these correlations in that higher dimensional space. And so we were curious about whether the machine could learn those sort of higher dimensional sets of correlations. And interestingly, if you train to learn all of the quantities simultaneously, then even with the methods that were relatively low accuracy, they were able to learn those quantities. So I think there's a lot of interesting future work. I won't go through this, but I'll just say, to echo Greg, that this project is just getting started. There's a lot of exciting work, and we would love to talk to any of you who might be interested in collaborating on this project with us. Thank you very much.
Oh, Paco.
So Rachel, I was wondering about the scatter. So do you expect that this will work at all? I mean, what about the butterfly effect? I mean, you might.
What about the what?
I think it's butterfly is called.
Oh, the butterfly effect.
So,
yes.
So there is some.
That's an interesting point. You have to consider, if you rerun the simulation, to what accuracy can you even predict a particular quantity? But 30-35%. The butterfly effect is usually much smaller than that, right? It's more like 10%, I think, typically for these kinds of quantities. I should also, I didn't mention this. The work I very briefly presented was actually trying to learn predictions from semi-analytic models, not from hydro. Interestingly, many of these results are similar when you try to learn from hydro simulations. So you might think that semi-analytic models would be easier to learn because they're so much simpler, they're more tightly connected to the merger trees, but that doesn't seem to be the case, which is also quite interesting.
But in semi-analytics is deterministic. I mean, given
semi-analytics are deterministic. You use the same seed, you get the same answer. Yeah. No butterfly effect. But yeah, that's an important point when we try to do hydro.
Questions? Well, Rachel, I have a quick question. Yeah. I'm curious, like, what would be a dream goal if magically all these things work for like the mapping from dark matter to galaxy properties? Is it all properties?
What would I do with it?
No, is it all properties that you want to have a perfect mapping, or is it just specific properties you want to really drill down on?
So I think we have to be driven by the observations that we can anticipate having, right? So, like with learning the universe, we're focusing on galaxy surveys and CMB surveys. I'm also very interested in intensity mapping. So, C+ and CO and 21 centimeter intensity mapping. And I think there's enormous power in combining those different kinds of observations together. So that's one of my interests, is thinking about, how ways to cross-correlate these different kinds of observations to break degeneracies. And there's many degeneracies between the galaxy formation processes themselves, right? But then also, of course, the degeneracy between cosmology and baryonic processes. So I don't need everything, but I think we should, have a set of observables in our sites and try to be able to produce sort of a broad range of observables, not just one.
The questions. Well, if not, let's. Oh, sorry, I can't see her.
Yeah,
you're blocked exactly by the.
Yeah, exactly.
Please go.
Well, I just wanted to ask. So, the last question that you pose is sort of like, how does this generalize to other models? And I guess the pipeline assumes one model for galaxy formation and sort of machine learning approaches applied to that model. So in order to answer that question, you can answer whether or not it works by just comparing, two different models. But in order to generalize it, would you have to repeat the same thing on another model, or is there something smarter you can do? Because then you end up sort of with this huge computational expense?
No, that's exactly the question, right? So if you train your model on Lambda CDM with a certain set of galaxy formation models, could you then apply it to some other cosmology and would it work? I have no idea. Maybe Paco has some intuition for this, but yeah, that I think we would just have to try that and see how well it works.
Beyond whether or not it works, how do you correct for it if you assume that it doesn't quite work?
Well, you might have to retrain on each different model, right? Which, as you say, would then be kind of bad.
Yeah.
Yeah.
Oh, thank you. Yeah.
I mean, I thought what we want to do is to sort of do symbolic regression, which I think Anna's going to talk about, to get galaxy properties, see like what are the fundamental important stuff that we actually need to have a parameters on, and then we marginalize those for cosmological parameters. For galaxy formation variables, which you want to learn, I think there's a slightly different game to be played there, which I haven't thought about that.
And it may be, I think we already saw this already with Andrina's talk, right? That if you stay close to the space where, you sort of match observations, then it may work. If you go to some very extreme model, then it may break down, right? But then you probably don't care because that's not the universe, right?
Questions? Anyone online? All right, let's thank Rachel again. Anna, it's your turn. We're very happy to have Ana Maria Delgado to tell us about modeling galaxy halo connections with machine learning. She's coming from Harvard CFA, and she works with Jay and Borana, Sanek, Lars, and I. And Jay just defended. I don't know whether he's here, actually. He just defended and passed and become Dr. Wadika.
All right. Thank you, Shirley, for the introduction. Button. Okay, thank you. Thanks for having me, everyone. I am Ana Maria Delgado, as Shirley introduced me, and I'll be discussing modeling the galaxy halo connection with machine learning, which is a team effort from people at CFA, NYU, and CCA. Okay, so, all right. In our aspiration to answer some really tough questions that have been brought up here, such as like, how do we, what is dark energy? How do we constrain the cosmological parameters to an accuracy within 1%? The community has planned some sky surveys of unparalleled depth, which will give us data to a precision that we have never before seen. For example, 2 of such surveys will be the Euclid and the DESI survey, which will use photometry and spectroscopy to produce really large catalogs of, among other things, luminous red galaxies and emission line galaxies. And so what we want to do is we want to make sure that our theoretical models and our systematical uncertainties are robust enough to handle the precision needed for these data sets. Now, state-of-the-art hydrodynamical simulations such as Illustrious TNG provide a model that tells us what this galaxy halo connection is, right? And we can use these simulations such as TNG as a testing ground for our theory models. And in this work, we consider 2 primary statistics for the galaxy halo connection. And these are statistics that will be used by the aforementioned surveys. So one is the halo occupation distribution, which gives us the average number of galaxies per halo. And the other one is the 2-point correlation function, which quantifies the spatial distribution of galaxies. Oh, cool. I see my timer. Okay. So just to explain a little bit about what these models are, the halo occupation distribution, or as we just call the HOD. So our view of the large scale structure is that of like clumps of dark matter. And the HOD is a model for how the galactic matter is distributed within each of the dark matter clumps. It describes the probability distribution relating the mass of the dark matter halo to the number of galaxies that resides within this halo. And this is what we refer to as the standard HOD. So moving forward, when we talk about the standard HOD theory model, we're talking about this dark matter halo mass to galaxy that reside within the dark matter halo. So the next statistic that we use is the 2-point correlation function. You can use your predicted number of galaxies from the HOD to weigh your 2-point correlation function. This is what we do. And the 2-point correlation function measures how different our distribution is compared to a random distribution. So in this little cartoon, we have 2 dark matter halos, and they are separated at a distance r, and the correlation function just computes like this ratio of how many pairs of halos are at that distance r to how many pairs of random points are at that distance r, and is our distribution more clustered or less clustered than this random. Okay, so recalling that TNG can provide us with what this galaxy halo connection should be, and recalling that the theory predicts the number of galaxies depends only on the mass of the halo. Work such as that by Hajiska here has shown that there is a 15% discrepancy between the standard theory and TNG 300. So just to draw your attention, particular to the top panel of this plot, which is from Boreana's paper, we have here, on the x-axis, this is the radius from the center of a halo to, and on the y-axis is the correlation function times the radius square. And if we look particularly at I want to just kind of amplify the large scale, so anything above 1 megaparsec, we see that 15% discrepancy from TNG 300, which is in the red, to the standard HOD theory, the mass only theory, which is in the gray. So the question then becomes, how can we reduce this 15% discrepancy? So the literature has shown that this discrepancy can be reduced by incorporating secondary halo properties. Hajiska did this in the work from the plot that was previously shown. She does this by assigning galaxy numbers based on a rank ordering of secondary halo properties. So halo properties such as environment, concentration, velocity dispersion, etc. Then furthermore, Jay Whitaker in his recent paper used machine learning to model the neutral hydrogen content of a halo while also incorporating secondary halo properties. So in this work, we want to show that the galaxy halo connection can be improved by incorporating secondary halo properties. Now, because there are no first principles that currently exist as to which secondary halo properties to use, we use machine learning to do 2 things. First, we identify which of these secondary halo properties best minimize this 15% discrepancy, and we do this using a random forest regressor. And then the second step is to augment the standard HOD model using symbolic regression with simple equations that can incorporate the effects of these secondary halo properties. Okay, so we first start with the random forest regressor in order to identify these properties. Now, this plot just shows a ratio from our prediction. So we see here correlation function of random forest over the correlation function of TNG. If our model perfectly agrees with TNG, it will perfectly fit along this orange line here. And we found that the random forest, not only can it recover the standard HOD mass only, which is shown here in the green dotted line, but it is a very powerful algorithm and it is quite fast. So, and it can handle like a lot of dimensions. So we would systematically add a secondary halo property, such as environment, shear, spin, Vmax, velocity dispersion, etc., and try to kind of close this 15% gap. And what we found that from the random forest is that incorporating shear and environment, which we see this model and the black solid line, brings our model closer to that of TNG 300. Okay, we further want to do this work, and we want to connect this work to the types of catalogs that are targeted by the upcoming surveys, such as the ones talked about in the first slide. And so we therefore examine clustering at 2 redshifts at z equals 0 and z equals 0.8, and for LRG-like and ELG-like galaxies. So in this plot on the right, these 3 panels show our model that incorporates the 2 features selected by our random forest as being the most powerful ones, the environment and the shear of the halo. The top 2, and compared to TNG, of course. And the top 2 panels are for LRG-like galaxies at 2 different redshifts, and the bottom panel is just for ELG-like galaxies. And we can see that there is improvement in the LRG-like galaxies. In the ELG-like galaxies, at this point, we saw no kind of statistical change. So moving forward to the next step, we focus mainly on LRG-like galaxies. So in the next step, we use symbolic regression via the PyStar package, which was talked about yesterday by Miles Cranmer, to augment the standard HOD model. On the left, we have our standard HOD model. So it is broken up here into 2 equations, one that gives us the number of central galaxies that reside in a galaxy, and the bottom one gives us the number of satellites that reside in a halo. Did I say galaxy? They reside in a halo. And on the right, we have our augmented HOD models that have these multiplicative terms. And it is these multiplicative terms that were provided by the symbolic regression. And, feeding it the environment and the shear, well, we found that the environment really informs the central HOD model, and the shear really informs the satellite HOD. So here, delta and delta prime refer to the environment, Q prime refers to shear, and A is a constant. Okay, so let's try out these models, and these are the results. So comparing to TNG 300. So we see here that, so I updated these plots recently, and I forgot to change the legend for this talk. So, in the legend, equation 4a refers to the satellite HOD, and equation 4b refers to the central's HOD. So here we have our standard HOD model again, mass only in the green dotted line. And we see by incorporating, so keeping the standard HOD centrals, but incorporating our augmented HOD satellites, we do have some improvement, which is the blue solid line. But incorporating both the augmented centrals and satellites, incorporating both shear and environment, we are able to even further improve our results. Okay, so for some next steps, the Millennium TNG simulations are going to be coming out soon. Right now, there are, we're almost ready for a box that has 500 megaparsec per H on a side, which is about 15 times the volume of that of TNG 300, which is what we used in this work. And the next iteration after that will be 3 gigaparsec cube volume. So we can use these really fantastic, robust simulations to calibrate our models. And then another thing that can be done with this is we can test if against feedback parameters. So we can test whether our models are robust against different baryonic feedback parameters. So for example, with the camels, which has a range of feedback parameters, or using semi-analytic models, we could just test whether the models are robust against these. And so in summary, secondary halo properties can be modeled using machine learning, and symbolic regression can be used in aiding us to augment of the traditional theoretical models. And with that, I'll take questions.
Thanks for the nice talk. I have a question about how you're implementing the HOD. So does your model just affect the mean occupation number of the halos?
Yes, the average number of halos.
So do you put in any velocity biases for centrals and satellites? Because in analyses of actual galaxy clustering observations, if you don't include those parameters, it's very difficult to actually reproduce observations.
Yeah, we just use the standard HOD. How can I go back this way? Yeah. And here we just use the standard mass only HOD. And this is what we were aiming to augment as a first step.
And then, so for the positions of the satellites, for instance, you're just sampling, like an NFW profile.
The positions of the positions, everything comes from TNG 300. So
of the satellites.
So what all of our positions? So of our satellites, we just put them in the center.
I see.
Yeah, and this is why we're really kind of just focused on the 2 halo term. So our x-axis here, we start at 1 megaparsec and larger.
Okay.
Yeah.
Thanks.
Oh, and then Niraf. Yeah.
And this is a beautiful work. So this functional form that you got, do you know how this compare with? I think other people has tried to use assembly bias, like in Emulus. I mean, does this functional form more or less compare with what other people has been doing to model this secondary?
So I think that there are other works that do show that, for example, Boreana's work and Jay's work do incorporate environment and show that this really helps assembly bias, to kind of close this discrepancy that we're finding. And this is very much a first step. I am not claiming that this is the end-all be-all equation to anything. I am just showing that it can be done, or just contributing to other works that have shown that this can be done.
Niraf?
Hi. So nice talk.
Thank you.
I have one small question and then a follow-up question. So how many properties did you use for the random forest, and how many trees did you use?
How many trees? So we ended up using 50 trees. Properties, we went up to 7 properties, 8 properties. So all of the ones that we see here, of course, were used.
Mm-hmm.
These are 6. We also used concentration. We also used different definitions of environment. We compared many things, like anything that was like, if you were to check out the paper by Boreana, any of the secondary properties that she used, we also used. Anything that we found that our collaborators had used in the past.
Okay, so I have a follow-up question. Can you please go back to slide 12?
12. Yes.
So it might be just my opinion, but if you see the curves, they look more shifted than fitted.
Okay.
Getting my point? So in the upper one as well as the lower one, so your equation 4a plus 4b is more shifted towards the 1.0 horizontal than fitted, right? So it means that, and this equation is the one which includes additional parameters which were given to you by the random forest, right? And can you go back to the previous one, with the random forest features? Yeah, this one. So in here, the black one is again shifted, which is kind of closer to the perfect agreement, but it consists of shear, environment, and mass, right?
Correct.
So that means there might be another combination of these features possible that might result in a better fit than shift. Is that possible?
I don't see why not. Yeah. I also found that this looked a little bit more like just kind of some sort of like linear
shift.
Yes. Right. Yeah. So this is something that we're still discussing, and I'm discussing with different people, professors and whatnot, and getting some feedback on that. If you're asking, is your question, could there be other properties that could help?
My question is basically like, what I'm thinking is maybe this shifting is telling us something that might be there, but I don't know, I'm just like spitballing here, but I would say like a shifting then fitting is telling me that it might be just like a chance that you like those 3 particular features are helping it to shift, right? It's just a thought.
Yeah. Valid.
Yeah, thank you.
Burning questions? Did you raise your hand, Rachel? Quick one.
I did. This is a really minor thing, but it's hard to know exactly where the one halo term and the two halo term are crossing there. They're crossing right in there.
Yeah, they are.
So you could do something really simple, which is when you analyze TNG, just take all the satellites and stick them at the center, and then you'd have a more sort of one-to-one comparison.
Yeah, this is definitely what we did. We put our
I'm saying
the wrong way.
for your denominator, you could just sort of correct TNG, instead of keeping the satellites where they really are in TNG, just by hand put them at this. Does that make sense?
Yes.
Yeah, it's a small thing.
Oh, okay.
It would just make it easier to assess the accuracy.
Yeah. So the only reason we chose that is because we didn't. Oh my goodness, I'm going in the wrong direction. Is here. We just didn't find any change from the standard in the bottom panel here. So we're like, okay, I guess we'll just use LRG. Not really. Yeah. At this time, yeah.
Yeah.
Thank you.
We'll have Sultan Hassan telling us. Actually, Sultan has a project with Paco and Spergel and the Camels team on fast simulator for H1 maps using normalizing flows.
So green goes, right?
Green's the right way.
Means that also. So thank you for the organizers that's been really a great workshop so far. So the main motivation of this actually is, when you try machine learning, usually just you use a CNN or something just to get things out, and it's all usually easier to compress things and get the information out if you have like so much dimensions, right? But then the question is that can you expand this information, right? So if you have like just set of parameters, right, can you really link things to this parameter? And that's really what excited me to work on generative models, basically. So let me give you like the other motivation from what we know from all these coming surveys, right? So it has been decided by us through 2010 that the priority of things going looking for the first stars and galaxies, and there are so all these many experiments and many more are coming, and to try to explore these large scales and look at the H1 intensity mapping and H1 surveys. And so that's why it's also another motivating things is to try to develop some theoretical efforts in besides these observational efforts. So the main question is that we know all these experiments coming. So how would you extract the maximum information from these surveys, right? So we know that also most of the signal we are interested in are like really non-Gaussian. So you need to go beyond the power spectrum. And then the main idea is you need, right? I mean, if you want to extract the information, technically you want to be able to emulate things, and you want to, the most of the information happens in the 3D field and the 2D field, right? So you need to be able to emulate them in order to have a fast generation of these, to generate this data set very quickly, and then you can do inference at the level of the field. And as Bak showed you in his talk, when you do that, you can extract the information efficiently. However, this is not possible with these simulations now because it takes very long time to do. So you need to be able to make some emulators that are able to give you this, to generate, like from the parameter, you go directly to the 2D or 3D data sets, okay? So then that's why I became interested in generative models. One that is really rising, like it's rapidly growing in the use for these models in the field is normalizing flows. And people have talked about this, so I will go quickly about this. So it's you can use it the other way. So because it's kind of you try to learn a mapping between between a base function and complex transformation. So you could go also. It's a flow, so you can go back and forth. So you could basically generate models. So generate new diverse examples. So this is basically like fake human faces. Has been normalizing flow model trained on celeb A data set. So you can see some features. So it beautifully recovers these images. And at the same time, also you can do inference as likelihood inference by going to the other way around. So that's the beauty of these models. And this is the basic idea, is that you have a base model like base density, usually a Gaussian. You try to skew that Gaussian distribution by learning this mapping, and you get your signal. And the beauty is that now when you have this mapping, then each point in your Gaussian distribution is really linked to that complex distribution. So you can, after you learn this mapping, then when you draw random numbers from this distribution, each time you're getting new examples. And it's basically very simple. It's just the core of this method is just the change of the chain rule and the change of variables formula. So you need to decide what Jacobian you want to use in order to be invertible, and at the same time you need to be able to compute the determinant of that. So there are lots of normalizing flow models. We also heard yesterday by BUI, they have another model. So I use just the standard one that came first. So it's the masked auto regressive flow. So it's basically, it's a family of made, or the masked autoencoder density estimations. So basically, when we say autoregressive, it's a property that you want to ensure that in your model, all the future values depend only on the previous ones. And we will have shown that if you use like a normal autoencoder that compresses information and expand them again, you can apply some mask to the connections between the different layers, and then you might be able to ensure that your autoencoder now kind of autoregressive in that sense, because you are breaking the connection between things, and now only the future values will only depend on the previous steps. So then what happens now when you combine a family of these mates, you basically now you can have a more flexible model that can learn lots of more complex transformations. So then I decided to use the camels for that. So and then because the camels they have a diverse set of simulations, simple, Astrasty, so many of them, and I'm also interested in a very high redshift. So I'm using here maps at redshift of 6. And just I go to the simulation, I generate the H1 maps at redshift of 6. And what is nice here is that I don't really use the maps, So what I do basically, I flatten all the maps and I input them as one-dimensional vector. And by that, I lose information, right? Because I lose the correlation between the nearby pixels. But I was surprised that works for this level, and it's really amazing to see that. So okay, so let's go to the results. So this is here comparing the fake and the real. So of course, the real is the right, where you see the filament structure, very nice. This is the fake in the left. So looking at the large scale, you see that both models look roughly similar. Maybe the model fails on a small scale, but that we know by construction because I flatten all the input images. So that I wouldn't expect the model to capture this tight correlations, but still the correlation between the nearby pixels, but still you can see that on large scale, it looks very nice. It doesn't really look bad. So now we can go and quantify this at the level of some summary statistics, right? So you could basically select 2,000 maps from camels, then generate 2,000 maps from the H1 flow, which is the model this model. And then you can compare them at the level of the power spectrum or the BDF. So the BDF by the left, and this is the column density, the H1 column densities. What you see in solid is basically, this is the mean. So you have 2,000 images, you compute 2,000 histograms, then you take the mean and the standard deviation. This is what you see. The solid is the mean, and the shaded area is just the standard deviation around the 2,000 images. So what you see here, like at the level of the BDF, which is what the network has learned because I input flattened images, you see that it really, this is the one-to-one relation. So this is the relation between the two means, but the mean ratio, and you see that if you are interested in range between probably 10 to the 7 up to 10 to the 11, you kind of perfectly recover what you expect. Of course, we lose information because you see the variance. You cannot really capture the variance, and this is one of the problem in most of these machine learning models. You can't really get the scatter right, but you get the mean relation very well. Okay. Now, if you look at the power spectrum, it's the same experiment. You just compute 2,000 power spectra for all the maps in two sides, and then just plot the mean and the standard deviation. And as you see, as we expect that, you're getting really close on large scale to the right power, but then in small scales, of course, because you lose information. So now also it depends. So you could use this if you are interested on only on large scale signal, then that would be nice. That would be enough to do. And at the same time, training this model only takes like half an hour training on a single GPU, which is very, very fast. And getting new generation of images is very quick too. So now you want to condition on parameters. So what I showed you what I have shown you is just without conditioning any parameter, just learning the actual density of maps. Here we want to condition on the parameter, but before that, we don't want to just give information that is not relevant to the network. So then let's see in the camels, we have set of 6 parameters. So 2 of them, omega matter, omega sigma 8, which controls the cosmology. And then you have others 4 parameters that they control the feedback parameters. Then there is a 1P set, which is a very nice set in camels where they just vary 1 parameter each time. So one could just see how the variation happens in each one for the H1 maps and see how the BDF changes with respect to these parameters. So what you see here from that is that like probably the second row, all these parameters, they don't really affect the BDF of H1 maps at that redshift. There is a bit of variation in the last parameter, which controls the stellar feedback, the mass that ejected from galaxies. But the most variation I see at the level of H1 maps is for omega matter and sigma 8, and this is what I decided to condition my maps with. Okay, so now let's see. So now you can redo the same exercise, right? Generating 2,000 maps. After you have to retrain the model to learn the condition on parameters. You can redo your analysis again by generating 2,000 maps. You find what is for different values for omega matter and sigma 8. And then you compute again what is the mean of your maps at that time, and also what is the standard deviation. And what you see here is that for the for the PDF and for the power spectrum, the power spectrum changes, right? So that's nice. But the question is that also it changes to the predicted level, right? So you know that if you increase your omega matter and sigma 8, then your power spectrum should go up, right? And at the same time, your BDF should go up. But then is it really going to the right direction? That was a question we have been thinking of. And then what we thought we should do to validate that is we could basically just to have a quick test where you could take all the maps in camels and just produce all the power spectrum for all these maps, and then train just a simple MLP, like multiple perceptron layers network, and just to learn how the power spectrum changes with parameters, right? And now let's compare that when we use the same parameters in the H1 flow and see how the two models compare. And this is what you see in what you see in dashed lines is what I predict from in the dashed lines is what the H1 flow predicts. And then in the solid lines, this is what the expectation when you do this at the level of when you train MLB from the camels, which is basically the true of the camels, which is the MLB basically will give you the mean for that. But then if you change the parameters at different panels, as you see that the H1 flow responds more or less accurately to the variation on the parameters. So it works. So let me conclude by that it's what I realized that this is a really powerful technique to do that. It trains very fast, and one could you generate new diverse examples very, very quickly. And then after you condition on the parameters, now I could use this model because I could link it easily to MC, and I could do or the likelihood free inference or any technique to just do inference very quickly than just running the actual simulations. And I think with that, I would stop here.
Michael?
Yeah, thanks for that. I'm completely understood the architecture that you're using.
Yes.
Something that looks coherent as a 2D.
Yeah, so it generates the flattened output, and then I reshape it again. It looks like an image, and this is good.
And the images have periodic boundary conditions, right?
Yes.
So you're basically like generating a sort of periodic 1D function that seemingly, when you unflatten it, generates an image back. I'm just wondering, like there are some masking procedures that can actually sweep 2D puzzle manner as well. So that could be something.
Yeah. So I think I just did I did this exercise for the fun of it and just to see whether it would work and how fast it is. It's also to learn how these models work. But yeah, I mean the model that I showed you earlier, also when I was discussing this with Miles a long time ago. This model I showed you earlier, this is called not flow, it's called glow. So it's basically it's the same technique, but it works on 2D. So they you try to keep the 2D information by convolving to the on 2D images. Yeah. So I'm pretty sure if I use something similar to that, it would the result would be much nicer. But at least from what I see here is that like what I am impressed with is that like at the level of these column densities, so that's why you see also the recovery in the PDF is much nicer than the power spectrum because of flattening the images. But you see at the end that if you look at the large scale, it looks quite very close to each other. So you could basically believe that it learns this on larger scale. Small scale, yeah, we lose that.
1 second, when I just read out a question from online, is that okay? They wanted to ask the size of the 2D map that you flattened.
Yeah, so the 2D maps, because it's the camels, right? So the volume is like 25 megaparsec per little edge each side. And I guess the pixels I'm using here is 64 by 64 pixels.
Do you want to go for the next question?
Thanks for your talk. Normalizing flows are awesome. I was wondering if you, in the end, you talked about using this for inferring posteriors. Since you have a 64 by 64 data vector, then if you were to try to get the posterior, in this example, it would be your parameter space would be 3 parameters, right? And then a 64 times 64 conditional variable space. Have you do you expect to encounter any issues as you scale up the dimensionality that dramatically?
Like if I use a bigger image, like higher resolution images?
No, just even with 64 times 64.
To do inference with that?
Yeah.
Yeah, so so that could be an issue. That's true. But I didn't try, so I don't know. But if you also take that generator and plug it back again to do like likelihood free inference, they have shown these like likelihood free inference you don't need so many steps. And at the same time, I have only 2 parameters. So my dimension is like the parameters that I condition on is only 2. So that wouldn't really add much. But I see your point that if I probably condition on the 6, that might be a problem. But if you condition on 2, might be much easier to get. So
thanks.
Any questions, Narash?
can you please tell me about how did you like normalize your maps like before feeding it to the network?
Yeah, so I standardize them. I think you take the log, of course, because otherwise the small column densities you wouldn't resolve. So I log them, and then after that, after the log, I subtract the mean and divide.
Yeah. So actually, that's what I'm curious about. So did you like take like for each image? Did you take the mean and standard deviation of that image?
No, I didn't do that. Sorry, so that was wrong. So what I did is that because I use like the hyperbolic tan as my activation and for each the layers for all layers. So I basically put all my range from -1 to 1. So
did you use like all the images for that, or just for each image? Did you rescale each image?
No. I scale the whole training set. So that the mean is so you if you want to scale from -1 to 1, then you have to take the maximum and the minimum, and that maximum and the minimum for the whole training set. You don't do it for each one, because you need to know that when you scale things, they should scale with respect to parameters.
So it's kind of from each image you subtract the mean image.
No. Yeah. So you take the mean for the whole training.
Okay. Yeah. Okay. Thank you.
Yeah.
Questions? If not, it concludes the last talk of the day.